Let's take a look now at two simple problems that can be solved with the principle of energy conservation, but that require us to acknowledge the role of rotational kinetic energy. And to that end, we'll start by revisiting the Atwood machine. Previously, we made a couple of assumptions about the Atwood machine. We said that the pulley was both frictionless and massless. We're still going to pretend as if the pulley is frictionless, but this time we'll acknowledge that the pulley may have mass, and that means it's going to have some rotational inertia. So we'll suppose that this mass begins near the floor. Here's a heavier mass. I'll call them mass A and mass B. And some invisible hand is supporting this here. But at t equals 0, we pull our hand away and allow the system to accelerate. So if this one's more massive, of course, we expect it to accelerate downwards, and this one should accelerate up. And I'll just quote a result that we developed months ago now. For a massless and frictionless pulley, I recall that the acceleration of these two, the magnitude of the acceleration, you just take the difference in the masses, divide by their sum, and you multiply that by the free fall acceleration, g. Simple result. We looked at a video from the MIT demonstration series demonstrating this. And we can use kinematics to figure out, after mass A descends through a height h, we can calculate easily how quickly it should be going, how quickly this thing should be moving just before it strikes the floor. Remember, if the acceleration is constant, which it appears to be, there's no mention of time here, then we can use our constant acceleration kinematics. So I'm going to call down the positive y direction, since I expect this one to be moving down. And then I can say that here, I'll label sometimes T0 is when the masses are released and allowed to accelerate, and T1 will be when mass A strikes the floor, or just before it strikes the floor. That's implied. And then we can use these subscripts to set up our kinematic equation. And I'm not going to write the subscript y because this is a one-dimensional problem. So I'm talking about y coordinates here, but the velocity at time 1 squared minus the velocity at time 0 squared would be 2 times the acceleration times the displacement. Well, here's our theoretical acceleration, and the displacement, regardless of where we put the origin, the displacement is down by h units. That would be positive h. And since we start from rest, we can cross that out, take the square root, and the speed of this thing at the bottom should just be the familiar root. We've got a 2h, and then we'd plug this quantity in. So instead of root 2gh, which is the speed of an object after free falling through a height h, we've got, let's see here, root 2 times difference over sum. Notice that this quantity in parentheses is unitless, kilograms cancel, 2gh. So the velocity is modified from the free fall speed by the presence of this term in parentheses. So I'm going to put this off to the side and compare this to the result that we get for the slightly more sophisticated problem where we acknowledge that the pulley may have mass. And since we're now talking about rotational inertia, the distribution of the mass matters. I'll give this an outer radius of r, and I'll call its mass mp for mass of the pulley. And I'm not going to specify the actual distribution of mass here. If you think back to a couple of the labs we did we even get to do these labs before the COVID, the move to remote instruction? I don't remember, but if this was a very lightweight plastic pulley, then the mass might be concentrated at the rim, kind of like a thin hoop. Or it could have a relatively massive axle or core with some lightweight spokes, in which case it's kind of in between a thin hoop and a solid disc. So let's just leave it general and suppose that for the pulley, it's got some rotational inertia, which I'll call I. And hopefully you recall from a previous video, it's going to be some number times mr squared. and I called that number c, nothing to do with the speed of light, which is usually what that letter is reserved for. This is the mass of the pulley. Whoops. In this problem, I'm calling it m sub p. Mass of the pulley, radius, outer radius of the pulley. Now, if this were a solid disk, this would be a 1/2. If this were a thin hoop, this would be a 1 because all of the mass is out at radius r. Anything else, it's got to be some number between 0 and 1. I'm not even going to put less than or equal to because it's impossible to actually have all the mass at the edge. All right, and I mentioned that we can solve this using the principle of energy conservation. Now, a couple chapters ago, your book introduced this equation. Work done by external forces it shows up as in two possible ways. Either it's dissipated thermally, or it shows up as a change in mechanical energy. And we can still use this equation despite the fact that we've now introduced a new form of mechanical energy. That's the rotational kinetic energy. That energy is included in this term. So even though the chapter that introduced this equation didn't discuss rotational energy, it's still part of this overall scheme. Now in this problem, the emphasis here, so I'm gonna get rid of this now because we're acknowledging that the pulley does have mass, but we're still going to make the assumption that the pulley is frictionless. And these things, we don't expect these masses to fall very quickly, so air drag is insignificant. Sneeze break, hold on. And if we can ignore air drag and friction within the bearings of the pulley, in real life, you would have some friction, then that means we don't have to worry about dissipative forces. And remember, the increase in thermal energy is just the negative of the work done by dissipative forces, because dissipative work is always negative. Negative, negative means increase in thermal energy. So let's get rid of that term. And also, remember, the way your book categorizes things, external forces are any forces that are not gravity, springs, kinetic friction, air drag. That's it. If it's not those four, then it's called external work. I don't see any such forces in this problem. The only force doing any work here really is gravity. Now, there's a subtle point here. As far as mass B is concerned, the tension pulls up. As far as mass A is concerned, the tension also pulls up. And believe it or not, these two tensions are not equal. We haven't talked about torque yet, but if this thing really does have mass, then in order to get it to turn, you have to apply unbalanced torques on it. You've got to torque it harder in the clockwise direction than you do in the counterclockwise direction. And that means the tensions would have to be unequal. And those tensions also do work. But if I recall, if you were to account for that work, you'd find that the two works cancel. Yeah, let's think about it. This one's moving down while the tension pulls up. So this tension's doing negative work on mass A. Mass B is moving up and the tension pulls up, so this tension is doing positive work. You would find that those two works sum to 0. So they just disappear from the equation. We don't even need to worry about them. I've actually never confirmed that for myself, but I'm confident that that's the case. So external work is 0. This is really a conservation of mechanical energy problem. And a lot of books would just say delta E instead of delta E sub mechanical. It's just a notation issue. Okay, since I've defined the two times as 0 and 1, let me dispense with the subscript mech now and just say that the total energy at time 0 must be the total energy at time 1. There is no dissipation of mechanical energy. What are the three types of mechanical energy in this problem? There's gravitational energy. There's translational kinetic, right? The masses are moving up and down. They're translating. That's just 1/2 mv squared. But we've also got to account for this kinetic energy associated with the spinning of the pulley. So if you want to be really formal, you could say gravitational energy at time 0 plus K translational at time 0 plus K Rotes-Magotes at time 0 equals, and then you'd have similar terms on the right side. I ran out of space there because I'm not very good at thinking ahead when it comes to using the space on the paper. All right, now here would be the time to acknowledge which of these are 0, so we don't actually have to write the formulas. And before you can do that, you have to decide where to put your origin. Pick some place that's sensible. Pick an origin that's going to simplify the algebra a little bit. If I put the origin down here, y equals 0. Ooh, and I just realized, if you're going to use this formula for gravitational potential energy, you must call up that's opposite gravity, the positive direction. So this result is still applicable. I used downward in order to derive this result, but if we're going to apply energy conservation using this formula for gravity, you do need to call up positive, or you're going to run into problems. And who needs more problems in life at this point? Okay, so by putting the origin down here, I can say that mass B's initial energy is 0. And maybe you're thinking, hey, wait a minute. The center of mass is actually a little bit above the floor. Fine, you're right. You would have to put the origin so that the center of mass of B begins there and the center of mass of A ends there. But those are technicalities that we don't, let's just not get too detailed here. Pretend that these blocks are small enough where their center of mass might as well just be any point on the block. Okay, what are the non-zero energies at the beginning? Well, nothing's moving yet, so we don't have to worry about any of the kinetic energies. The only non-zero energy really would be the potential energy of mass A, because it's at a height h above the floor. And the floor is where the potential energy is 0 for any of the masses. Now, it is true that the pulley, which is above the floor, has potential energy as well, but the pulley is not going to move up or down. So if you included that gravity term, you'd have potential energy on this side for the pulley, potential energy on this side for the pulley, and those numbers would be the same because the height of the pulley doesn't change, and you could just subtract them from both sides. So let's just forget about that as well. So all we've really got here would be the potential energy of mass A gravitationally at time 0. Now, once this thing strikes the floor, mass A now has a potential energy of 0. You'd plug in a y coordinate of 0 for mass A, and mass B would now be up here at height h. Remember, because the string doesn't stretch, that's string theory. Okay, that's not really string theory, but because it doesn't stretch, if mass A drops by h, mass B has to rise by h. So mass B will now have the gravitational energy at time 1, but then they've also both got translational energy. So I would have to say K, I'm not going to write K trans A1. I'll just put K A1 because the masses can only have translational energy. I don't need to worry about the distinction between translation and rotation. They're both going to be moving because they're attached to the same string. KB1 is mass B's kinetic energy of translation at time 1. And then we will also have K rotational at time 1. And this will be the rotational energy of the pulley. So this is not a bad place to start. This is a little more formal, probably better for maximizing your partial credit. And now I'll plug in the actual formulas. Mass A times G times its initial y coordinate of h above the floor. So if we had numbers here, we could plug those in and figure out how many joules of energy are in this system, how many joules of mechanical energy we have to work with. At time 1, mass B is the one up at height h, mass B, G, H. And here's what, I'm gonna, with some foresight here, simplify this slightly. Both of these are moving at the same speed. Remember, string theory, if the string can't stretch, these have to be moving at the same speed. If one was moving faster than the other, the string would be stretching or shrinking. And we're making the assumption that that doesn't happen. So since they both have the same speed at time 1, which I'll call V1, I can factor out that V squared and just write this as 1/2 times the total mass of MA plus MB V1 squared. And then lastly, do you remember the formula for rotational kinetic energy? In translation, we use this formula. For rotation, the m gets replaced by rotational inertia, and linear speed, if you want to call it that, gets replaced by rotational speed. So you shouldn't have any trouble memorizing the kinetic energy of a rigid rotating object. It's got to be rigid if it's got a well-defined moment of inertia. So 1/2 moment of inertia time, or of the pulley, times the rotational speed at time 1 squared. Now suppose we were given, let me specify the quantities that might be given in a problem like this. Let's say we know the mass of the mass A, that's redundant, mass B, the moment of inertia of the pulley, the radius of the pulley, heck, why not the mass of the pulley? You know, these are all related. And the initial height of mass A above the floor. Suppose we'd like to find how fast the two of those blocks are going right before mass, which was it, mass A? Right before mass A strikes the floor. Well, then let's look at this one equation that we've written and count the unknowns. Mass is given, height is given, mass given. Again, mass is given. We don't know this. This is what we're looking for. And we also don't know this. So technically we have two unknowns in a single equation. You can't solve one equation for two unknowns. We need a second equation. Many of the problems in the semester amount to exactly that. You identify the number of unknowns. That's the number of equations that you need to write. And then you go looking for those equations. And it's usually some combination of an acceleration constraint, Newton's laws, and then later in this chapter, we're going to get to an equation involving torque. Well, the second equation comes from relating these two. So I haven't actually talked about this yet. This is a good excuse to talk about this. We did talk about rolling without slipping, and this is a lot like that. So I'm going to say a string unraveling without slipping. Okay. So suppose you've got a mass hanging here, and there's a whole bunch of turns of this string. So this thing's free to rotate, and the string would unwrap. And then at some later time, the mass is down here. Okay, so we've just picked up this much extra string. Okay. Can I do this right? Yeah. Okay, so I'm gonna imagine that you've painted a radius onto the pulley right about here. Do you see that as this thing rotates clockwise, the length of extra string that we acquire here has to be equal to the arc length turn through. So if we're going to turn through angle theta to get to here, so this radius will end up right here, then this arc length has to equal the extra length of the string. You could probably come up with a better drawing there. In other words, the arc length has to equal, well, since this thing is moving down through a height h, I'll call it delta y. And for now, I'll call this the positive direction again to make this simpler. So S is equal to the vertical displacement of the block. But we know that S can be written in terms of the radius of the pulley and the angle through which it turned. So that would be R theta. And I really should call this delta theta, change in theta. So R delta theta is equal to the vertical displacement. Those two lengths are the same. Well, I can easily turn this into a velocity, because if I take the vertical displacement of the block and divide it by the amount of time it took to move through that displacement, I'd have to do the same thing over here, right? Divide both sides by the same quantity. And now you recognize number of radians per second. This is the angular speed. That's how quickly it's rotating in radians per second. So we call that R omega. And delta y over delta t, that's simply v, the velocity of the falling object. So you've seen it before. You've seen this for tangential velocity of a point on a rigid object is its distance from the axis of rotation times omega. That was one use of this formula. Then we saw the condition for rolling without slipping. We saw that the center of mass moves at a velocity. If you're talking about a solid disk, for instance, rolling down a hill, the velocity of the center of mass is the radius of the disk times the angular speed. That's if it's not slipping. And now we've got a third use of this formula. I'm just going to write it like this, and it's understood. This is the velocity of the mass that's hanging and falling from the pulley. This is the angular speed of the pulley. So as this speed increases or decreases, it goes up and down with omega. Same equation, or it looks the same, but it's really three different equations applying to three different physical scenarios. All right, so now we can relate these two. The speed of mass A as it strikes is very simply related to the rotational speed of the pulley at the moment mass A strikes the floor. The pulley is going to spin faster and faster as that block goes faster and faster. Two fasters, is that redundant? And now let's solve for V1. Why don't I collect these two together on that side? They both have a GH in common, so MA minus MB GH equals, and let's see, omega 1 squared would be R squared omega squared. So I could actually say omega 1 would be V1 R over R. Does that work? Yeah. This is getting sloppy here, but omega is the same. Solve this for omega. Omega is the same as V1 over R. So when I square omega, omega 1 squared would be V squared over R squared. Okay, so I've actually got a 1/2 total mass times speed squared plus 1/2 I times V1 squared over R squared. Okay, this comes from the translational kinetic energy. This comes from the rotational energy. Now, we can simplify this a little bit. We can make this R squared go away because remember the moment of inertia has an R squared in it. So let me rewrite this now. So that we can get one nice little formula at the end. One half, and then the moment of inertia is that general constant, which I've called C. Your book doesn't necessarily call it that, times mass of the pulley, times radius squared of the pulley, times V1 squared over R squared. And now we see that the R squareds go away. And let me just simplify the right side. What do we have in common here? We've got a factor of 1/2 in common and a V1 squared. So this would be 1/2 times, and I'll factor out MA plus MB plus C mass of the pulley, V1 squared. And we're done now. The last step would be to divide both sides by this garbage, take the square root. Here's what I find. V1 would be the square root of, we still have a root 2 GH, but there's an additional term, root 2 times, that would be difference in the masses over, whoops, sorry about that. Just yell at me when that happens. Yell at your computer screen. 2GH. And there it is. We've used the principle of energy conservation to find a general formula for the speed at which these masses are moving right before mass A strikes the ground. And let's compare that to the previous result for the massless pulley. If the pulley has no mass, then what we're missing here is this term. So it's always kind of nice to look at a more general problem and then take the result of that general problem and show that it includes, as a special case, the simpler problem that we first looked at. Now, would we expect this to go to 0 if the pulley were massless? Yeah, I mean, one way of looking at it would be if it's massless, then MP is 0, and this just goes away, and we would recover the simpler expression. Now, there's another way of thinking about it also. What if the pulley did have mass, but the mass, how do I put this? It's like, what if all the mass were concentrated at the center? So it's like an extremely lightweight plastic wheel with a massive metal axle. If all the mass is here, then when you go to calculate the moment of inertia by taking each little piece of mass, multiplying by the square of its distance, well, for all these values of radius, for those values of R, the mass of these little pieces presumably would be 0 because I'm imagining that it's super lightweight plastic. So those would contribute nothing to the integral. The only pieces of mass that would contribute to the integral would be the pieces at the axle, but their values of R are practically 0. So this would come out to be basically 0. And you could write that as C times MR squared, where C would be 0. So if the pulley is either massless or it has all of its mass concentrated at the center, either way, this goes to 0, and you would recover the familiar expression. If you hear me clapping, it's just to activate the mic so that you don't miss the first couple words of what I say. Not that it's that important. Next up is another loop-the-loop problem. And this problem always reminds me of a demo I tried to do at Cal State Fullerton once upon a time, because we actually had a track like this in the stockroom and something like a ping pong ball that we dropped down. And in front of the class, I calculated the minimum height from which you would have to drop this ball so that it would actually make it around the loop. Of course, if you dropped it from high enough, it would make it around the loop and be going faster than it needs to be going. But we've talked at length this semester about the minimum speed required at the top. So what's the bare minimum height from which you have to drop it to make it around the loop, supposing that there's no air drag to speak of? And again, that's a little silly because on its way down, this ball will have some of its mechanical energy dissipated by air drag. And there's also going to be some rolling friction, I would call it. Remember, well, I was going to say remember, but we haven't talked about this yet. In order to get an object to roll, we'll talk about this more once we've discussed torque. But if this thing is not rotating, if it's not rolling, and then it starts to roll, that means it's spinning. So it wasn't spinning, if you started it from rest, let it go, it goes from not spinning to spinning. How do you get this thing to spin? Doesn't there have to be a force pushing that way on the disc? If there were no force pushing that way, it's not going to start to turn. And of course, that force could be none other than static friction. It's static because I'm imagining a perfect rolling motion. The disc or ball is not supposed to be sliding. If it was sliding, that would be kinetic friction. So there has to be friction in the problem if this thing is rolling. But even though the center of mass is translating against the static friction, if you look at the point of contact where the friction is actually applied, this point does not move. That's not obvious, maybe, to a lot of you, but this point is momentarily stationary. The top of the rolling disc is moving the fastest. It turns out that the center of mass is moving at half the speed of the top, and this point, for a moment, is not moving. So as this thing rolls, the ball or disc is just replacing its point of contact. And since this force is not being applied to a moving particle, it's being applied to a stationary particle, then the work done is actually zero. The work done by static friction would be the integral of the static friction force dotted with dr. But if you look at where it's applied, there is no displacement. So this just goes to zero. Technically, the work done by static friction is zero. Now, if you look at the work that the static friction does on the center of mass, then you would not get zero. That's a very nuanced subject that evaded my understanding for a while because it doesn't get treated in these books usually. Let's not worry about that now. So all of that to say that there actually is friction in this problem. There must be static friction to get this thing rolling, but that's not a dissipative force. So we're going to assume that air drag is insignificant and rolling friction is insignificant. And back to the Cal State Fullerton story, we did this problem on the board. We found the minimum height. I put the ball at that height and drum roll, it just went, didn't even make it to the top, wasn't even close. So my first thought was, okay, that means there's significant air drag. And it wasn't a ping pong ball, it was more massive than that. So I think we tried to account briefly for that, and it still didn't explain why it didn't make it anywhere close to the top. And then stupid me, I realized I had totally neglected the rotational energy. So let's take that into account now. And we'll still start with this equation. External work is dissipation of thermal energy plus the change in mechanical energy. And we'll say, since the only forces here that are actually doing work, or the only force is gravity, because think about it, I just explained why static friction doesn't do work, and the displacement of the ball is always tangent to the track, but the normal force is normal to the track, and that means no work is being done by the normal force. That would be the only force that could possibly count as external. So the only force doing work here is gravity, no dissipative forces, and that means that the change in mechanical energy is zero. That's like the most precise possible way we could go about arguing that the energy, and when we say energy, we really mean mechanical energy, is conserved. So let's define our times. T0, ball is dropped or released. This isn't New Year's. That sounds like Times Square, ball is dropped. T1, the ball reaches the top of the loop. Loop the loop. I used to think it was loop-de-loop, but the phrase is actually loop the loop with 2 hyphens. That was probably an old circus attraction. Okay. Before we start writing potential energies, we have to pick our coordinate system. If you want to use MGY, you've got to call up the positive Y direction. And I'm going to put the origin down here. You could put the origin up here. This place and this place would be the two sensible choices, but you must call up positive if you're going to use MGY. So I will say that the gravitational energy at time 0, I'm not even bothering to write the kinetic energy of translation and the kinetic energy of rotation at time 0 because they're both 0. The ball is not moving yet and it's not rotating. And here's where it's easy to make a mistake. Don't forget that when the ball gets up here, it still has gravitational energy. If I put the origin down here, then when it gets here, its gravitational energy is not 0. Now you could actually put the origin here, and then your energy here would, for gravity, would be 0, and that might seem like a simplification, but then you'd have to figure out what this distance is in terms of h and r. So I think the easiest choice is just to put the origin here. So we still have some gravitational energy at time 1. We also have translational energy, k trans at 1 plus k rots magots at time 1. And that's it. That's our statement of energy conservation. What is this? Where'd this come from? Oh, that's Fs. Now, before we go evaluating the translational energy at the top of the loop, we need to know how fast the ball needs to be going at the top of the loop. And we've seen this many times. So let me just do this separately. From circular dynamics, the minimum speed required at the top is the one for which the normal force goes to 0. So the centripetal acceleration comes from gravity alone. And I'm just going to quote the results since we've seen this many times. Gravity alone must provide the centripetal acceleration. I'm skipping the step where I write some of the forces in the r direction equals mass times acceleration in the r direction, and I plug in the forces, and I argue that n goes to 0. You wind up with this. So G is equal to mv squared over r. I'm sorry, not mv squared. That would be force. Mass times acceleration is force. This is just acceleration. So v1 squared over r. And now we know that the square of v1 is just rg. We've seen that before. That's our minimum speed. I'm not going to call it v1 min, so I don't clutter the equation with subscripts. Okay, so the gravitational energy initially, the whole point is to find this required minimum height. I could call it h min, I'll just call it h. So we're up at some unknown height. And how about I use lowercase m for the mass of the ball? And note carefully, I'm reserving big R for the radius of the loop. So I have to use lowercase r for the radius of the ball. All right. So the initial gravity energy of the ball up there at height h is mgh. And when it gets to the top of the loop, it's got some kinetic energy of translation 1/2 m v1 squared. It's also got rotational energy 1/2 I omega 1 squared, where this would be the moment of inertia, the rotational inertia of the ball. And lastly, I almost forgot the gravity energy up here. So what is the height of this point above the floor? And I'm realizing, you may also be realizing, once again, technically the center of mass of the ball is not actually a distance above the floor equal to the diameter of the loop. It's a little bit lower than that, right? So if you really wanted to account for that and be precise, your equation would be more complicated. But let's just pretend that the diameter of this ball is really small compared to the diameter of the loop. So we're not introducing much error by ignoring that difficulty. mg, what's the height here? Well, this would be the diameter, which is double the radius, so 2r. Okay, we're supposed to find h, assuming that everything else is given. Well, we just found an expression for v1 in order to barely make it around the loop, but we don't know omega 1. And well, for the moment of inertia, once again, I'm just going to leave it general. It's some number times the mass of the ball times the radius of the ball squared. See how I'm careful to use the appropriate notation for this problem, where this is some number, C is some number between 0 and 1. And at the end, we can evaluate this for a couple particular cases, like a solid disk, in which case C is 1/2, and also a sphere, in which case C is 2/5. We haven't talked about that yet. Okay, MGH equals 1/2 M, whoops. All right, you know what, I'll save that step, because first we need to recognize, okay, I is gonna be CMR squared. We need to recognize, this is the rotational inertia. Once again, we need to recognize that omega-1 is related to V1 for rolling without slipping. Rolling without slippage. The velocity of the center of mass is the radius of the ball times the rotational speed of the ball. Now, technically there's a cm here for center of mass, but in this problem, it's understood that the speed V1 at the top here, V1, that is the speed of the center of mass. We're talking about the center of the ball and how fast it's moving. Remember, because it's spinning, each part of the ball might have does have a different velocity, different direction, different magnitude. We're talking about how quickly the center of the ball is moving. So omega-1, if I solve this for omega, it's V over R. Omega squared would be V1 over R, lowercase r, be careful, it's the radius of the ball, squared, and then plus our mg times 2r. So it's easy to make mistakes with the notation here. And I think you'll notice that every term in this equation has an m. Kind of interesting. It doesn't matter how massive the ball is, so whether it's made out of glass or lead. And can we simplify here? Well, do you see that the r squared here, it gets canceled by the r squared in the denominator? So I've got a 1/2 V1 squared plus a 1/2 C V1 squared. Beautiful. Plus 2GR. And we're nearing the end here. Well, the end of the problem. Let's factor out, I'm going to put all this G stuff on the other side. GH minus 2GR. I'm going to factor out 1/2 V1 squared here. So I get 1/2 times 1 plus C V1 squared. See what I did there? If you distribute, you can recover both of these. I put the 1/2 on the left side and the V1 squared on the right side. Okay. And now I'm realizing I didn't really need to put this over here. It would have been better left over here. So I'll put it back. GH is equal to 2GR plus 1/2 1 plus C. And here's where we can invoke the result from the dynamical part of the problem. The square of the speed at the top of that loop has to be RG. Aha. All right, and then we can make a further simplification. G appears in all three terms. That's gone too. All right, so this result does not depend on whether you're on planet Earth or the moon or a place with no gravity. Well, that's silly, because if there was no gravity, this thing would not fall down the track to begin with. So there has to be some gravity. And the height evidently has to be 2r plus 1/2 times 1 plus C times r. Can I factor some garbage out? Well, I can factor out an r, that's for sure. So 2 plus 1/2 plus 1/2 C times the radius. Of course, we're specifying the height in terms of the radius, right? The bigger the loop is, the higher the ball would be at the top, the higher you would need to drop the ball to begin with. So we're just about done here. Here, I'll finish this right here. 2.5, what is that, 5/2? So I can write this as H is equal to 5/2 plus 1/2 C times the radius. Okay. Well, without knowing the actual distribution of the mass of this ball or disc, we can't actually evaluate C. So let's look at just a couple special cases. And I want to point out something that I neglected to say in this problem. When I wrote this equation, where did it go? If you look back or think back to the discussion or the introduction of rotational inertia in that previous video, This is the rotational inertia of a circular or spherical object about an axis through its center, only if it's rotating about its center. Now, there's an alternative way of looking at this motion where this thing is really not rotating about its center. I'm just going to briefly mention it. There's two ways to think of the rolling of this disk, I'll call it, down the ramp. You could think of it as a simultaneous rotation about an axis through the center. So it's doing this while it's translating. And to me, that's the most intuitive. But you could alternatively describe it as merely a rotation, no translation, if you think about it as rotating about this axis. That makes sense? Imagine taking this thing and, like, if, I don't know, if you had it somehow attached to a rod coming out of the page right here so that it was free to rotate, you know, a moment later, it would be here. So it's going around, the center of mass is making a circle like this as the whole disk rotates. You can account for the instantaneous motion of this disk by imagining that it's rotating about that axis. Maybe that's hard for you to picture. And if you do that, then there's no need for the translation. So there's some theorem in more advanced mechanics that maybe was discovered in the 1800s or even the 1700s, which says that the instantaneous motion of any rigid object can be described as a pure rotation. I think that's the result, which is kind of surprising. But let's go with the more intuitive interpretation. It's rotating about an axis through the center while it's translating. And since it's about the center, we use, where did it go? We use this formula for the moment of inertia. Okay, I have yet to talk about the parallel axis theorem, which is presented in your book. Okay, for a solid disk, that constant c has a value of 1/2. Remember, 1/2 mr squared, so the height would be 5/2 plus 1/2 times 1/2. Well, that's 1/4, right? 5/2, isn't that 10/4? So that's 10/4 plus 1/4 times r. That would give us 11/4. Okay, that's not the result I was expecting, which is, well, let's see. 4 goes into 11 2 times, which would give us 8. There's 3 left over. 3 out of 4 is 0.75, so 2.75 times the radius. All right, well, 2 times the radius would be the diameter, so it's a little bit higher than the diameter of the track. So somewhere up here. Well, in actuality, that's not going to cut it because in real life, you would have to deal with friction. Now, that fraction doesn't look familiar to me, which makes me wonder if I forgot something. I may have. If you caught my error, email me. Now, if you wanted to figure out how high a sphere would have to be dropped from for a solid sphere, in other words, a ball, like a wooden ball, well, the moment of inertia for a solid sphere is 2/5. I think that might be derived in your book. We didn't do it because it requires a little more calculus. Instead of 1/2, it's 2/5 mr squared. You could use that for planet Earth as well. So that means this constant that I've been calling c has a value of 2/5 for the sphere. So the required height, since I originally left it in terms of c, would be 5/2 r plus 1/2 times 2/5. All right. Well, the 2's cancel, and that's 5/2 plus 1/5. Well, 5/2 is 2.5. 1/5 is 0.2. 2.5 plus 0.2 times r, 2.7. If you want to write it as a decimal fraction. Okay. That's not quite as high as the result for a disk. Hey, maybe that'll show up on Jeopardy, or you can impress your friends at a party. That would literally never happen, but the disk would have to be dropped from a slightly greater height than the ball. Why is that? Well, that tells us that for the disk, more of the mechanical energy shows up as rotation than it does for the sphere. And for that reason, you'd have to give it a little bit more potential energy to begin with. Okay, 2 good problems. They require several formulas that showed up in this chapter, and yet another application of the principle of energy conservation. And what do you know? I just found a demonstration on YouTube from the MIT group. So let's take a look here so you don't have to drag this or track this down yourself.
Yay!